Yeah, it's funny to do this talk as a conclusion today. Okay, so getting back to this talk, which is at the intersection of three things, and I find it very funny because today was supposed to be only on blockchain and AI, but what I heard was a lot of talk about formal verification as well, and proofs in semantics of programming languages. And it's exactly what this talk is about. So paradigm shift without the pain. There's good AI and bad AI, and here we're trying to find some good AI. So basically, how AI can the photographer be silent, please? And at the intersection of three things, so blockchain, AI, and semantics, we see now that we have two major innovations coming in. One innovation is blockchain that brings a lot of interesting properties, but as well, it brings complexity on the implementation side, and a global trend in AI, and I will focus on one thing in AI, and that thing is specifically how we use AI to write code and to generate programs, basically, program synthesis. And what is the role of programming languages in that? And I'll start with one fact, which I think we are living in a new era for programming, because 50 years ago, we were programming in assembly, and all the developers were supposed to have knowledge of the silicon level details, like the timings of the chips were important to be able to program. And there appeared a new generation of programming languages, such as C, for instance, and there are people who ridiculed programmers by saying, oh, you're just writing C, you're not a real programmer, you don't know how the silicon details work. And today, my take is that we are seeing the same thing for LLMs. And there's a lot of new developers who use ChatGPT or Claude and who basically write lines of code using AI, and they don't understand the content of these lines anymore. So we can tell it's bad, but if we do the same, let's say, comparison with assembly 50 years ago, maybe that's the way to be. Maybe developers will use LLM to write these programs. And that brings me to another thing, is languages accelerate innovation. We've seen it in the past, may it be Fortran, which accelerated numerical computing, Lisp for AI, and especially symbolic AI back then. By the way, they lost. And ADA in aerospace and defense, because powerful programming languages bring a new abstraction which accelerates the pace of innovation. And this is something that Paul Graham has said pretty explicitly in his book, Hackers and Painters. A company that gets software written faster and better will, among other things being equal, puts its competitor out of business. And this is an idea that you find, again, pretty well in Hadak and its co-authors like Simon Peyton-Jones and Philip Vladler in Edinburgh about the Haskell survey, with a lot of focus on the DSLs especially, and the DESL, the embedded DSLs that keep the syntax and the parser of Haskell itself, that basically we can use Haskell to accelerate the pace of innovation by writing DSLs. It turns out that more than 10 years ago, I created as well an experimental programming language called OPA. So we made an O'Reilly book and a few other things. And we had a radical approach to fully integrated web programming. And we solved one problem called the impedance mismatch, which was really strong back then when you wanted to write web application. It's that the client, the server, and the database would be written in completely different language with completely different assertions. And we tried to find one programming language that was fully functional, strongly statically typed, and that brought, let's say, a lot of simplicity. It even introduced byte for byte the JSX syntax. You can check it. It's very old. It's on GitHub. And we even formally verified some parts in the assistant Coq, because we're a French team back then. And so we did a lot of things, but that was not a gradually innovation. That was something that changed completely the way we program web application. It was very appealing to the top end of developers, like PhD students here at Stanford, or the developers at Facebook, especially back then. But what we witnessed is that changes happen more gradually with TypeScript, React, and GraphQL, which basically OPA was doing all three all put together. But all this required a lot of years and a high cost of developer outreach. And if you look at what is happening on blockchain today, there is some implementation complexity. I've been personally, there's papers saying that, and I've been speaking personally to a lot of teams at conferences, blockchain conferences, and many developers state that it's hard to get all the domain knowledge to go into blockchain development. Because especially one thing is very important is security. And we need to get the smart contract security, which is getting in order after a few years. So the best practices, the audits, formal verification sometimes, and as well the front end. And we've seen, for instance, with the Bybit attack, that just a very traditional Web 2 cybersecurity attack was sufficient to bring SAFE down. Just by replacing the front end through getting access to the AWS console. So it's still basically the very old OWASP top 10 of web vulnerabilities that applies today. So can a programming language help in that? If you look at the smart contracts, they're very well specified, thanks to Solidity. And this is, I think, a very important part in the traction of Ethereum in the ecosystem, just because it's very easy, in fact, to write good programs in Solidity, and it has the right properties for performance in particular. But JavaScript and TypeScript remain dominant for dApps and smart contracts front ends. And here we see a very clear lack of semantics, basically, for this business logic of the dApps. And this is something that Vitalik has written about. And he said that we should go beyond HTML and JavaScript and specifically mentions our work in the domain. So what we were set to write is a language that specifies and verifies the blockchain interaction. So this is our goal. And our goal is, let's say, to build a huge catalog of all the legitimate on-chain interactions so that any user, may it be an end user to a front end, which could be generated, or may it be AI agents that want to pick into a catalog of these interactions to do things on behalf of their users. And basically, it's the same goal. We need this catalog. But we also need some bits of formal verification or correctness proofs so that we can be sure that this catalog of on-chain interaction is, let's say, the right one. And we could even use ZK stacks, so basically for verifiable computation to prove that these interactions have been well built into what we call cold data bytes, which are the raw bytes that the blockchain accepts as inputs. And we can do this for two reasons, because it doesn't work with unbounded recursion, but we don't need unbounded recursion for many cases in blockchain interactions. And it relies on RPC data, so on data that comes from the blockchain, but we can use oracles for that. And this is something that, for instance, the Noir language by Aztec does. Just to give you an example, this is a sample interaction in our current target language, which we call LambdaScript, and which replaces about 1,000 lines of JavaScript code split in React hooks, etc., into just the simplest formalization of the business logic of interacting here with Uniswap v3, which is already complex because it has 4 contracts, the router, a quoter, and the 2 tokens themselves. So now we face a challenge. And that challenge is, how do we bring developers to that new technology, even if the technology is great? And there's been traditionally, and this was 50 years ago, but didn't change, or 45, developers prefer incremental changes. This has been studied in human psychology. And they may as well choose inferior, but well-marketed technology if they expect it to be dominant. And if they expect it to be dominant, it's because it's, let's say, brought together by large corporations, let's say technology which comes from Meta or technology which comes from Google. And basically, these are barriers to adoption. But we have two things that work in our favor. First, the blockchain developer community is still small, only 20K active monthly developers, according to the Electric Capital report. And that's why we see a lot as well as low-code solution that seems to be popular. So it's still time to change things. And especially as if we are building this catalog of on-chain interactions, basically it's a marketplace. And marketplaces have been studied by Tirole, which is a famous French researcher in economics, and basically said that the best way is to subsidize, if we're building a marketplace, so supply side is writing the specification and demand side is using them. And we should subsidize one side to attract the other, especially the supply side. That's easier. And that balances the interest of both groups. But these subsidies are very costly. The DevRel teams must educate developers, et cetera, et cetera. And here, and that's the proposal, basically we see a game changer. And that game changer is, what if we use AI and LLMs to just skip those adoption barriers and fill one of the side, and here it's the supply side, automatically and generate the code. So we could automate these specifications, and this is capabilities of writing code, which are put together by GitHub for their Copilot, and Claude in Anthropic, that in their, let's say, survey, basically, they really put forward the possibility to completely replace developers to automate code. So in our case, there's two things. First, we want languages that LLM can write easily. So that's the automatic generation, the synthesis of this interaction. And the second thing is languages that can read or reason about programs easily, and that's automated verification. So let's do part one, how we generate these interactions. So several things. So program synthesis has several challenges. So that's been studied by Liu last year. So basically telling that code repair is required. So basically you will ask LLMs to generate the first draft of the program, and that program will be imperfect, and you'll need some kind of workflow, basically agentic workflow, to do code repair and iterate on code repairs until you get a better specification. And there's another hurdle for us, for DSL, it's the lack of data sets. We have very few data sets in our own DSL compared to hundreds of millions of lines of Python code. So even if Python is, let's say, not as well adapted for LLMs to reason about, the thing is they have so much more data that basically we can compute probabilistic model and somehow get good results. But still, what we found out is we focus on optimizing our language design for LLM, which we did, by bringing domain-specific abstractions, which are very easy to catch up for LLMs. Purely functional programming, it's considerably easier, and we've made toy experiments that we will publish on that by using very tiny LLMs. They can understand functional programming easier than imperative programming if you take away the pre-existing data set and pre-existing knowledge. Same for strong static typing. And we've seen that adding type annotation at pre-printing accelerates the performance considerably as well of these tiny LLM models, such as order independent declarations. And something that's very funny as well is simple identifiers. So if you use tiny LLMs, if you use complex and meaningless identifier, let's say your variable has an identifier that is A, B, C, D, 66, that will be much harder for the LLMs to reason about, and it will make more errors than if your identifiers are just A, B, C, D, and V1, V2, V3. And that's really interesting, and of course, the smaller the LLM, the easier it is to see. And of course, adding explicit typing and structure pre-printing is something that has been studied as well. So it's Chen and OpenAI as well had a hint on this. So these are, as I told, our early experiments, and we will publish our own results. So this is really fresh. This is before we even submit the paper. But we've seen even more than a 2-4% gain. So we need to confirm everything. But apparently, these kind of simple functional programming languages are really understood very quickly by LLMs, and it improves the accuracy of simple tests with tiny LLMs pretty quickly. So here it comes to this synthesis of programs, and we've been designing basically a way to put everything we know about the smart contract, so the Solidity source code, the ABI, even the front-end code, to try to extract an interaction from it. And then we have, and this is fully probabilistic, like we have no control over what the model here, of course, not a small one, the biggest, the better. But we have no control on the output. So then we have three phases of first compilation and static typing, then simulation, and then verification that enables to check whether these tentative interactions are valid or not, and if they're not, then we rework them until they're successful. And basically, we're seeing, let's say, promising results, like simple interactions can be written by these agentic workflows. So this was very surprising. We thought early on that we were going to need way more examples before we could do that. Another thing is some details about the automated verification. And so you've seen probably black spatula or yes, no error. Those are projects that try to detect errors in a totally different domain in research papers, but they got a lot of publicity because they were published in Nature this week. And this is really interesting because of the domain, they don't have enough formalization of their problem, so they just throw LLM at it and find some errors. And it kind of works. But if we have an automated way of verifying correctness, and it's the fourth speech about formal verification here today, at least. I just heard bits. Then we can do much more. So, of course, there's several projects which I like to mention in that space. There's Lean Copilot, which basically can automate already 3 out of 4 of the steps on proofs. So it means it's applied for mathematical proofs here. And basically, it means that for many proofs, it requires 2 human steps, and all the rest is automated. And there is another paper which, as a Frenchman, I like a lot. It's Cobblestone because it's made in Coq, our, let's say, historic French proof assistant. And Cobblestone does not only apply to math, but as well to verifying properties in programs. And they do it by just combining partial proofs. So basically what they do is they try to have multiple runs on the automated verification. And when they have bits of the proof, they combine them together, and they considerably improve the state of the art on some data sets of formal verification. And I can add some details on that paper because I looked at some of the proofs, and it's very interesting that the automated proofs sometimes are nicer than the human one we had manually put in the library, for instance, the graph library of Coq. And they are shorter, and they don't require, let's say, externalities. So this is how basically we can verify blockchain interaction. So let me temper expectation here. The things we verify automatically are extremely narrow. Like mostly it's parameter consistency. We are just putting the right parameter in the right order. And that's already, that's a very small thing to verify, but that's very helpful to have it automated. And as well as data flow integrity, which comes almost for free with the functional programming, and atomicity and error handling as well, because we have our very small evaluator, which is as itself purely functional, and that basically checks that whenever there's an error, it propagates until the end of the program. And the last thing, and that's my last slide before the conclusion, is another thing what we're trying to do is learn from a few examples. So that was my PhD, in fact, in machine learning a long time ago, and where we used unsupervised learning to extract some properties, to generalize sequence structure, to improve, in fact, the learning in a supervised way with small models. And it's very funny because now there's a huge trend of papers doing this for LLMs in evaluation. And somehow it's related to another thing. This was the S1 paper, which made a lot of noise, and I think was made by a researcher here at Stanford as well, is that we can use smaller models, so reduce the amount of work at training time, but increase the amount of work at inference time with test time scaling. So basically, less labeled examples and more computing power for inference. And that's a very promising way as well, because especially in our case, again, we're trying to write specification, and we have very, very few examples to start with. So that's the conclusion, is that we are really trying to build for the blockchain AI-driven era. And I'm very happy that this happens, because it solves a huge pain that we would have if we were not able to have this vision where we can automate generating these interactions and provide, let's say, safer interactions on chain for everybody. A few things so on the future direction. So scalability now is pretty okay. That's less than 1 billion contract. So if we manage to have all this process automated easily, and let's say at pretty low cost, we can think that we could have many of these contracts already modeled somehow for interactions. And there's, of course, more work to do on reliability and attestations as well. So we are working with a project called Ethereum Attestation Service, which is a public good, and which provides human attestations. And that's the very last conclusion, is that if we automate everything, we'll keep humans in the loop just to attest that the work of the AI looks good enough, and then we'll compute scores out of it. So thanks a lot, and that's the end of this.